Thank you very much. So today I want to tell you a little bit of IMS, intrinsic mirror symmetry, complementing a little bit of Michel's talks he already told you about. So this is something developed by Gross-Siebert, and it aims to tell algebra geometrically what the mirror to given local BR should be as spec of some algebra of theta functions and I will tell you how do we obtain this algebra in some concrete examples over some affine. It's actually over some formal, you will get some formal scheme, generally C over some infinite power series. Okay, so there is this construction of Gross-Siebert given any local BR pair consisting of a smooth projective variety X and reduced anti-canonical normal crossing divisor D, telling you how to construct the mirror as a formal scheme. And here, any x by any x, we denote the monoid of integral points inside the Mori cone of x, which is the cone of effective Kerr classes. Okay, so I will tell you in some examples how do we construct this algebra, and I will stick on the assumption that xt is maximal, as Michel was mentioning. This amounts to assuming that D has a deepest strata, so it means in 2 dimension, it means D is singular. In arbitrary dimension, it means D has a 0-dimensional stratum. And this is the assumption in many of the Gross-Siebert papers. We need this, and Michel will tell you a situation like when this is not true, like if they look at P2 and the elliptic curve where they assume D is smooth, how they can handle those cases situations. So this will be important for us today for my talk. So I will go through some concrete examples. So any toric variety is a maximal local BR pair with its toric boundary divisor, X toric D toric boundary divisor, which is the union of divisors that are fixed under the torus section, the natural anti-canonical divisor. Then this will be a maximal local BR pair. So if you look at P2, as Conan mentioned, with the 3 lines as its toric divisor, then what is the concrete algebra the Gross-Siebert program will give, you can ask even in this situation. So let me call this Y, this family. What is Y? So to construct Y in this toric situation, what you need is 2 things. So to answer this, so you first need the tropicalization of XD. If you have a toric variety with its toric boundary, as you mentioned, you just get the toric fan, which is just in a normal fan for the polytope Conan drew for P2. So this is the toric fun sigma in R2. And the second thing you need, in addition to the toric fun, to write down equations for this is the data of a PL function on, so let me write this phi from let me see, Rn to the Grothendieck group associated to this monoid, the smallest group containing it, and here is the, in this case, it's 2. In general, you can look at any dimensional toric variety, so it's the dimension of your fun, real dimension of your fun. And you define this piecewise linear function, so this is up to a constant function this is uniquely determined by specifying its kinks along codimension 1 strata in the tropicalization. So here, in this example we are going through, you need to say what the kinks of your PL function should be. And there's a natural way to tell what the kinks of this PL function should be, because every ray there is going to correspond to a divisor in your toric variety. As Conan drew the picture, you have these circles gluing together to a sphere in the P2 case. And you're taking the Kerr class of that divisor, like in the P2 case, you have this fun, which is the inner fun of the polytope Conan drew, and every ray corresponds to a P1, which is what he drew, where the circles give you a sphere. Okay. So let me call this class of this each P1L. So I will specify the data of the kinks as L. In this case, the Morricone, because Picard rank of P2 is one-dimensional. And I will say it's generated as a monoid by this L. Okay. And now, when in the toric situation, knowing just these two tells you a way to write down the equation of the mirror. So to do that, you will define the monoid of integral points about the graph of phi. So P by M, phi of M plus Q, such that M is in Zn in the square and Z2, and Q is in any X group. So this is the monoid of integral points about the graph of phi. And then it naturally contains this monoid NE, so because NEX is contained in P, in particular, if you take the specs, the spec CP has a natural map to this. And this is your ring of theta functions in this case. And this is the spec, this affine scheme of 0y. Whenever you're in this situation, you don't need to worry about the formal formal things, generally we said you have a formal scheme. Whenever you have x minus d is affine, you get an honest spec there. Okay, so if you write down concretely the equations of what this should be, for P2, you can do it using so-called broken lines in the fun to easily write down. So this is going to be a toric variety, which will be a family of surfaces, and you can write down so as an algebra, the generators of this ring of theta functions are theta functions defined by theta mi at a point P by z2 mi phi mi. So here P is a general point, so take P a general point in your tropicalization. So in the case of P2, you can take any point here or in this cone. And you will have as many generators as you have as you have rays. So we have 3 rays. I will have 3 generators, M1, 1, 0, M2, 0, 1, and M3, negative 1, negative 1. So my ring of theta functions in this example will have 3 generators corresponding to these. So these are primitive ray generators of the rays in sigma. And just by notation, we will often write this tuple as c to mi times, just to use a different variable, we will use t to phi of mi. Okay, so this is going to be an element of okay, let me write concretely what these theta functions are, and in a minute when I define canonical wall structures, I will tell you where in which algebra they live. Okay, so in this example, I have 3 of them, theta 1, 0, theta 0, 1, and theta negative 1, negative 1. Theta 1, 0, if you follow this recipe, it's just going to be z2, 1, 0. Because my PL function, once I specify its kinks, I said it's uniquely defined up to a constant function. And in this calculation, what we always assume that you're taking a general point in a chamber where my PL function here is 0. So such that phi is 0 on the chamber on the maximal cell containing phi. Containing P. And then if you follow the recipe, you will just get Z2, 1, 0, which I will call X. Theta 0, 1, Z2, 0, 1, I will call it Y. Theta negative 1, negative 1 is Z2, negative 1, negative 1 times, if you will lead phi minus 1, minus 1, it will be L. So I will have T to L. So this is X inverse, Y inverse times T to L. So these are the three generators of your algebra. And then you can write down concretely the equations of your mirror. So your mirror is going to be given by the spec of these three theta functions, 1, 0, 0, 1, negative 1, negative 1, modulo this equation. And there's one equation, if you multiply both three of them, x inverse, y inverse will cancel out. The product of three of them will just be equal to T to L. Okay, so this is what this algebraic recipe of Gros-Seibert will produce, and then you can ask a lot of questions. Is it compatible with other proposals of mirror symmetry and so on? And you can discuss more of those if you wish, and discussion sessions. But do ask me at this point if you have any questions. Okay, so the question is, what if I don't have a toric variety? So when I have a toric variety, this is easy. By now you can just write down the equation just easily by knowing the PL function and on the fan, and the toric fan. So what if you don't have a toric variety is the question. And the way, maybe I should specify, there is an easy way to write down this equation. We usually don't look at this formula. We just look at broken lines, which are, in the toric situation, which are just line segments. They never broke if you have a toric variety, which are line segments coming from infinity, from the directions of these rays, and ending up at P. So if you come from infinity towards here, in this direction 1, 0, you will have a ray like this, and this will correspond to the theta function 1, 0, which is coming from the x direction without hitting anywhere where your PL function has a kink. So the first theta function is x, the second theta function is y. The third theta function comes from here, but because to reach P, it hits this line, it gets a contribution from the kink here. So there's a combinatorial recipe saying when your theta functions should get a contribution from a kink. And if you take your point P not on this chamber, but either here or here, you will get up to isomorphism, the same thing, the same result. Okay, so the question is, what do we do in the non-toric case? Okay, so in this situation, I need some additional data. I similarly need the tropicalization of XD, which is going to be a cone complex we talked about. You can, in easiest terms, describe it as the dual cone complex of D and X. So this is a cone complex where you trade every codimension k strata of D by a k-dimensional cone. So for instance, if you have in P2 the union of three divisors, so this is a codimension 2 strata inside P2. For this strata, you put a 2-dimensional real cone. For this one, you put a real 2-dimensional cone, and for this one, you also put a real 2-dimensional cone. And you can see if you don't impose a maximal condition, XD to be maximal, some things will go wrong. And we say XD is maximal if D is a 0-dimensional strata, because only in this case you can ensure that the tropicalization has the maximal dimension as maximal as possible, which is equal to the complex dimension of X. Okay, and apart from the tropicalization, the second thing I need is again the analog of a PL function, what we call a multi-valued PL function. Which is from the tropicalization again to any X group. And the notion of multi-valued function is a confusing notion. There is no well-defined function really. So what you should think of this notion as just the data of kinks. Data of a bunch of kinks along codimension 1 locus in the tropicalization. And again, the codimension, yeah.
Complex lives inside X as well.
This dual Kohn complex of D is one way to describe topologically.
Where is that picture sitting?
It's an abstract Kohn complex at the moment, as the way I define it, but there are different ways on how to define the tropicalization of XD. So one way to define, you will get the same thing as an abstract Kohn complex if you follow the Kohn complex from M bar r greater or equal 0. You will get the same thing, the same abstract Kohn complex. In our recent papers, we define it in a way, like if you read our papers with Mark, in a way that it sits automatically embedded inside some Rn by choosing a basis and then defining it. That's one way to do it. And there is also, at the moment, by tropicalization, I just mean the abstract Kohn complex. And of course, it doesn't even need to look like the toric fan, but you can always impose an integral affine structure to embed it somewhere and to make it look like the really toric fan. So what we show is actually, apart from a codimension 2 locus at any dimension, there's a natural integral affine structure with some singularities along codimension 2 strata and such local ABRs. So you can naturally embed it somewhere and Rn, and there's some more structure in the tropicalization. Okay, so there's this data of kinks, and the third thing you need is wall structure, canonical wall structure. This is given by tuples, union of tuples F rho, where rhos are codimension 1 subsets of the tropicalization. And F rho is of this form X, a function of this form X k tau n v beta t to beta z to minus v. Okay, I will now tell you where this lives. So these are particular in the toric situation. Okay, I will tell you where this is. This is in C gamma formal NEX. So this is a formal power series in variables of the form t to beta, where beta is an effective Kerr class. And gamma is the lattice of integral tangent vectors. On MR, where your tropicalization lives. In the real space associated to your lattice, this is like where your tropicalization is living. So the elements C to minus V are here, where V is a vector in M. Okay. So there are these functions, and I need to tell you what everything here is. So here, k tau is just a constant. And tau is the type of an A1 curve what we call an A1 curve. Yesterday when I told you about the data of a type of log maps, tau is the same tau. And we will look at particular log maps that we call A1 curves to obtain this algebra. So tau is the type of an what we call A1 curve in XT, and an A1 curve in XT is the image of a stable map to XT touching T at a single point. XT with only one point touching T. So if you have a toric variety, there will be no curve, no A1 curve at all. Because if you look at P2, for instance, if you look at any degree D curve, say if you look at a line, it will touch here if you want it to touch here at one point, but it will necessarily touch here and here too. So due to topological reasons, if a curve in a toric variety touches the boundary at a single point, it will necessarily touch also other points on the boundary. So there are no such curves in toric local Abel pairs. So this becomes only interesting if you have something non-toric. So if you look at blob of P2 at a non-toric point, then you will get an exceptional curve E. This is an A1 curve because it touches the boundary at a single point. And if you take your boundary, so if you let your XD to be the strict transform of your toric boundary, E is a particular, like any exceptional curve is a particular example of an A1 curve, but there are many, many more A1 curves apart from exceptional curves. Like if you look at the strict transform of a line passing through this point corresponding to the point conundrum over P2 and this point, then you will get another curve of class L minus E. And this will also be an A1 curve. It again touches your boundary at a single point. So Grossi-Seibert EMS proposes that if you want to understand the equations of the mirror, what you need is the data of all these A1 curves. And all these will be encoded in the tropicalization of XT. So it's a natural thing, because if you can imagine you know how to construct toric varieties combinatorially from like polytopes, fans, and if you do like toric blow-ups, you will just chop off and at an edge corresponding to the exceptional curves. So non-torically, I still need the data of exceptional curves to, in some way, keep track of what I should do to construct the geometry. But there are more curves that I need, which behave similar to exceptional curves. Okay, so beta. Let me continue explaining this. So I have beta here, minus V here. So minus V. So the tropicalization of such curves in R2, so if you are in the two-dimensional situation, the tropicalization of an A1 curve will look like a ray because it has one irreducible component and it has one contact point. So if you want to draw a rough picture of the tropicalization, So the tropicalization of, like naively, this curve will look like a ray, and the tropicalization of this curve will also look like a ray. And minus v is the direction, is the contact order. So this determines the contact data. So minus v is the direction of this, is determined by the direction of this ray. V, if some sign convention, this minus v is the contact data for your A1 curve with the boundary. So it determines the contact data. Because in your tropicalization, if you take any ray in the direction of, say, AB, in the direction V, and if so, if this is the if this is a divisor with primitive direction rho I and rho j, if assume V is A times rho I plus B times rho j, then geometrically, what we want is to look at curves which have intersection number A with di and B with dj, the divisors. So we want A1 curves with contact order A with di and B with dj. So V determines the contact data. So in your tropicalization, any direction determines contact orders. So you can view the tropicalization as a cone complex where every integral point here determines some contact data. Okay. And then beta, as usual, is a homology class here. Beta is an H2 XZ, and this is a count of A1 curves of class beta. So of type tau and class beta with contact orders given by V. So and V beta is the number of all A1 curves whose image is of class beta, and type tau. So the type tau here in 2 dimensions just amounts to specifying V. In particular, it includes contact data V. In 2 dimensions, it's just essentially the same as the data of V. Okay, so let me tell you concretely in this example here what is these functions and what is the equation of the mirror. So in this example, there are only 2 A1 curves, and you can concretely write the canonical scattering diagram and the equation of the mirror. And then I will tell you what the subtlety in 3 dimension will be. So here, the canonical scattering diagram, to define the canonical scattering diagram, I will take the tropicalization of this. If you take the dual cone complex of this, you will again have these 3 cones. But as mentioned, there's more structure than just an abstract cone complex. There's an integral affine structure with singularities here, actually. On which Conan it's experts on, so I will just say very rough words. So this structure you can totally determine. You can determine from the geometry, in particular just the intersection numbers of D, of components of D. So here, before blowing up this non-toric point, you had 3 lines on the boundary with intersection numbers 1. Once you blow up, this one will have intersection number 0. And then you want to, similar to toric geometry, draw this tropicalization in such a way so that this will have no more intersection, self-intersection 1 but 0. To do that, you would need to, like, you can put an integral affine singularity here, and imagine you chop this off and glue this together to here. So there is what we call a focus-focus singularity at the origin and the tropicalization and the affine structure. And then to write down the equations of the mirror, what you do is, again, you specify the kinks of the PL function. So here, again, it's L. But once you blow up, this became L minus E. So here you have kink L minus E. And then what we're going to do is to input the additional data of these wall crossing functions, and you can take any ray and attach a function which will be non-trivial as long as there's going to be an A1 curve of that type. So you can check in this example, only for 2 rays you will get non-trivial functions, only for these 2. So you will need to add this ray, the data of this ray and this ray in your tropicalization, and attach to these rays some functions, so which will be of the form 1 plus t to the ex in this direction, and 1 plus t to the L minus e x inverse in this direction. If I got the signs hopefully correctly. Okay, and now this is a canonical wall structure, so this is all you need to be able to write down the equations of what your mirror should look like. Okay, so you can pick an arbitrary point in any chamber. It doesn't matter because it's a consistent structure, which amounts to saying you will always get isomorphic algebra whatever point you pick. If you pick your point here, again, it will be generated by 3 functions related to the fact that it's a simple geometry in 2D. So the generators will just be theta 1, 0 corresponding to the ray generators again. So you will have 3 theta functions, theta 0, 1, and theta negative 1, negative 1. And you can write concretely what these should be. So to write theta 1, 0, you're approaching, I think I changed my convention on how to draw the fun. So this point is now 0, negative 1. Sorry about that. This point is negative 1, 0. This point is 1, 1. So I have theta 0, negative 1, theta negative 1, 0, and theta 1, 1. So I will write an algebra generated by three theta functions corresponding to primitive integral points on these initial rays of my toric variety. And to write this, I look at this point P, and so I come from these directions. So if I want to write theta 0, negative 1, I come to P from this direction and stop at P. And you see, if you come to P from this direction, this is the direction of z to 0, negative 1. If you again assume I call z to 1, 0, x, and z to 0, 1, y, this will be like y inverse times, because to approach P, you cross this wall here, you need to multiply it with this function. So you multiply it with 1 plus t to ex, which will give you xy inverse, sorry, y inverse times 1 plus t, this thing. Okay. I will write down the equation. So theta 0 minus 1 is y inverse times this function. Theta negative 1, 0. To write theta negative 1, 0, you come from this direction. Okay, but the thing is, when you come from this direction, okay, I think there's some subtlety here. There's the singularity of the integral affine structure. You're crossing the singularity. And then I'm sorry, I might get confused. Can you double check? Because what we do is never really write the theta functions in the tropicalizations where you have these singularities because it's very subtle. We always push them away and write equations in a part where we no more have singularities. So if you come from this direction, you start your life with z2 negative 1, 0, which is x inverse. And then you do not cross any wall, but you cross this kink, so you do get a contribution from this kink, but I'm still confused if you cross the singularity. I'm not sure if this x inverse should change, because it's the monodromy invariant direction. If you would come from here, that would change. Okay, so then if you come from here, you hit nothing. So theta 1, 1 will just be xy, z2 1, 1, which will be xy. Does this look correct? Yeah, it does look correct. Okay, the mirror equation should look like this because I had calculated this before. Okay. So there's a subtlety here. Whenever you have tropicalizations for non-toric things, one needs to be careful because when you cross through the singularity, we were lucky here, it was the monodromy invariant direction, it didn't change anything, so I just said x inverse. But if I would need to come from a direction like here, then I would need to take into account there's some monodromy. Okay, in this case, nothing happened. So my mirror equation is just, see, these three theta functions. 0, negative 1, negative 1, 0. 1, 1. Modulo, if you take the product of these, now you just don't get t to l, but you get something more interesting, the product of these three theta functions. One plus t to L times, if you take the product of these, you will get t to L times 1 plus t to e times x. T to L times 1 plus t to e times x, and x was, okay, I think I should have calculated something wrongly because x is nowhere. The sign convention. Okay, that's better. And then you need to write this again as a theta function. So you will get t to L minus e times x inverse t to L times x inverse, which was your theta 1. So if you write this equation just using theta functions, you will get t to L plus theta e times theta 1. sorry, -1, 0. Does that look? Okay. Can double check this calculation. I'm sorry about that. I used a slightly different convention on how to write this in my notes. I'm sorry, I messed up with the signs, I think.
1 equals -1 anyway.
Yeah, I appreciate that. So, okay. I had taken in my notes this E, which should, is it okay? The equation?
Right,
Up to sign, okay, whatever. Okay, so in this case, the tropicalization would look like this, and you would put the singularity of the affine structure here, and if you take a point P here, so this was kink L minus E. I will just double check with the other convention. This was L, this was L. And my wall crossing functions here were 1 plus T to EX and 1 plus T to L minus E X inverse. And here you can check if you write theta 1, 0, 0, 1, and -1, -1. Theta 1, 0 hits nothing, it is just x, theta 0, 1. Now this time it really does cross this integral affine singularity, and if you come from this direction, because you hit the singularity, you continue here. And now you no more have y, but this time you really need to write it as xy. Because to come to this point, you come from this direction, but the integral affine singularity tells you to go there in the xy direction. And then theta -1 is x inverse y inverse, because you come just from here to approach this point. You only cross this kink, so you start your life with x inverse y inverse. And then you just cross this wall, 1 plus T to L minus E. So the wall, gosh. Okay, you cross the kink. You have one contribution of T to L minus E, and then you also cross the wall. So you multiply it with the kink, L minus E. And then you also multiply it with the wall crossing function, which was 1 plus x times T to E. Okay, so this should be the correct thing. And now if you multiply all three of them, you see you will get the product of them, theta, the product of all these three theta functions, theta 0, 1 times theta -1, -1 is really equal to T to L minus E times 1 plus theta 1, 0 times T to E. One plus theta 1, 0 times T to E. Okay, so this is the correct equation. If one puts the correct sign conventions and does carefully, one should get the same thing from the other picture. Sorry about that. And you can see you always get, when E is not effective a priori, but if you multiply by L minus E, you get T to L as a coefficient. So the miracle is whenever you write these equations, all your coefficients turn out to be Kerr classes which are effective if you do the multiplication. Okay, so did I start at 2:30? Okay, so I will just take a couple of minutes to tell what goes wrong So here, in 2 dimension, the count of A1 curves, this moduli space, has nice virtual dimension, 0 expected dimension matches. So in higher dimension, I will just tell you the subtleties, and finally, in the next lecture, I will tell you how do we calculate equations of mirrors to higher dimensional local bios, which is what we did together with Marcus. So if you look at the moduli space of all A1 curves in XD, so I will denote it by M V tau x beta. So this is the moduli space of A1 curves in XD. With one marked point of contact theta V, with one marked point of contact theta V, then you can calculate its dimension. This has expected dimension x minus 3. If you calculate it, you will get beta times C1, the log tangent bundle of x, and plus number of marked points. This is a general way to calculate the dimension. In our case, this will vanish, and you will just get dimension x minus 2. So in the 2-dimensional case, calculating the log chromatin invariance given by counts of A1 curves is easier because you will have 0-dimensional moduli spaces. In higher dimensions, it's more subtle. So what is true, though, is for a type tau, if your moduli space is log smooth, which is too much to ask for in general, but if you assume that x beta is log smooth, then the strata of A1 curves, so this moduli space is stratified, and the codimension of the strata of A1 curves of type tau, so tau v x beta, is equal to the dimension of the basic monoid that we talked of yesterday. So this is the strata of A1 curves in this moduli space of a given type tau. A1 curves of type tau. So there's some general machinery of log geometry related to tropicalization and reading of the dimension of the basic monoids in terms of the corresponding tropical moduli space. And there's this relationship that is expected if things are log smooth. So if you believe in this, what you need in higher dimensions, even if you don't have a 0-dimensional moduli space, you can count 0-dimensional strata by counting A1 curves where this has the correct dimension. So you would count A1 curves where the basic monoid. So count A1 curves with the dimension of basic monoids is dimension x minus 2. If you do this, this amounts to calculating 0-dimensional strata in this moduli space. So this is a technical part in the whole story. So you can count curves with a given type, and I will tell you how to do that. But there's one subtlety. Generally, this is not log smooth. This is not true. Generally, And to overcome this subtlety, you don't actually count curves on X. You need to look at an artin fun associated to X, which is an artin stack, and you count curves there. So we need to work with artin funs in general. That I will not talk about. It's due to the subtlety that this moduli space is generally not log smooth. You need to change your moduli space. Okay, but I will just give an example to illustrate what it means to count curves which have basic monoids higher rank. So this amounts to geometrically, you look at curves which fall into the divisor, which are as better as possible. And in higher dimension, typically, there comes up an additional worry that this contact data does not need to be positive. In higher dimension, you can have negative contact data. And in 2 minutes, I will finish. I will just give an example to give an idea in higher dimension how you can have negative contact data and that kind of thing happening. So, example, if you look at the toric variety first, dp7 times p1. So this is a toric variety. You obtain dp7 by blowing up p2 at 2 points. Let me draw it as I drew here, here, and here. And then you can take the product of this with P1, which amounts to taking the product of this with an interval. So this is roughly the toric momentum point-up you will obtain for dp7 times P1. So this is the P1 direction. So I take the product of this thing with an interval. And then you can blow up a line inside this, P1 fiber on this P1, which is vertical here. Okay, and then if you do this, if you blow up this line, you will get a family of exceptional curves over here. And at some point, this family of exceptional curves, if you draw this section, at some point, this family of exceptional curves will break into 2 pieces and they will fall into here and here. So you will have also the strict transform of curves passing through it here. If you take the limit, they will break and to fall into the boundary divisor.
When you draw that, this is reducible or all
So-
are reducible? Like that?
Yes, so right. So here these are curves, exceptional curves, and these are curves of class L minus E, going to the other side here. And in the limit, they fall into here. And I do claim this curve that falls into here has intersection, negative intersection when it falls into this divisor. And if you plot this tropically, so if you plot this whole picture tropically, you can see it. So tropically, you will have like the fan of this times the fan of P1. And if you tropically plot this curve falling into here, the tropicalization will actually look like a family of rays here in this case. And you can see, as we said before, if you write this as rho 1, rho 2, corresponding to this divisor D1 and D2, which is corresponding to this side and this side, this is in this direction, so any of these rays is like a sum of rho 2 minus rho 1. So there's a -1 factor here. So this curve log geometrically, if you calculate the intersection number with the divisor corresponding to this side and this side, it will be -1 and 1. So log geometrically, using like tropical geometry, you can tell what the intersection numbers should be, and they will, when they fall, they will have get negative intersection numbers. And we can, like tropically I told you how to see intersection numbers, but we can interpret everything tropical in terms of the Gauss sheaf that we mentioned, in terms of log data and I think it's, sorry. I also have a Swiss watch, but I'm still not Swiss. Very proud of it. So.
Okay.